I hope you can see the screen. Yesterday, actually, I faced huge problem in hearing issues and the network issues. So, if you have any such issue, you cannot hear me or you cannot see me, then you call me over phone. Otherwise, in PowerPoint presentation, when I am using PowerPoint presentation, I am not able to see this Google Meet screen. So, I shall not be able to know that whether I am online or offline in that way. So, I hope you can see the screen. Can you see the screen? And
Yes,
around
ma'am.
150, you write your name and roll number in the chat box, right? Not, around 150, not now. So HVDC transmission. So still now we have learned that about the HVAC transmission, and we have actually shifted from DC transmission to AC transmission because DC transmission and the most of the equipments of our utility actually that we use are AC. So it is better to use AC. And along with that, AC have several advantages also. It has one disadvantage that it has reactive power issues. That is unwanted power in power transmission. Otherwise, it is advantageous in many aspects. Firstly, we can step up or step down the voltage very easily using AC. But that is not so easy in case of DC applications. So that is one limitation. At the same time, when we are using AC quantities, we are supplying current or voltage in AC. Then, when there is AC current or voltage has a zero crossing, right? So, current or voltage will cross zero, and our frequency is 50 hertz. So, this total wavelength is 20 millisecond. Is not it 1 by 50 seconds? So, it is 20 millisecond. So if we assume that fault has occurred near to peak or anywhere within 10 millisecond, we shall get one zero crossing, right? So if the current is during fault, current is very high, so we have to disconnect the circuit. So if we want to disconnect the circuit at a very high current, so there will be arcing, there will be energy loss. Now, if we can disconnect the circuit near to zero crossing, then that problem will be less. So that facility is available in case of AC currents. That is totally absent in case of DC current. Okay. And I hope you know the relation between AC current and DC current. Say average value of an AC current is the equivalent DC current, right? So in that way, we can convert it. And DC current will obviously more than the AC current. DC value of AC current is more than its own value. So in that way, actually the AC has some advantages, but the main disadvantage is the reactive power issues. And we cannot get rid of that. Even with compensation or all other means, this will be there. So to get rid of that, we can use the HVDC transmission only for transmission so that we can avoid that reactive power problem because the voltage drop in a power transmission line will mostly depend on the reactive power loss or reactive power demand in the system, so that we can be controlled. If we make the reactive power zero, then ideally there will be no voltage drop due to the reactive power deviations. So that is the main reason that why we use the um, HVDC. There are so many other advantages that may be the sub part of the issues that I have discussed right now. So that is readily available, listed in the book. So you can read there. It may be listed in this note also. You may read there. Otherwise, you can read from the book. But the main advantage of AC is it has zero crossing, and we can step up or step down very easily. And the main disadvantage is its reactive power issues, reactance and reactive power issues. We cannot get rid of that. That's why HVDC transmission is preferred nowadays. But HVDC transmission also has limitation. For DC, current is steady. So for the same thing, if the current it is DC, then current is steady, right? So there is no zero crossing. So during the fault, current will be further higher than this value. So we have to disrupt that current. Okay. So it is difficult. So at a very high voltage, it is very difficult to disconnect a circuit during fault in case of HVDC transmission, right? So what is done actually? It is made that the voltage developed is become is made zero, so that current becomes zero, because if the voltage is not there, then from where the current will come? Generation is made zero, or voltage developed is made zero. So in that way, that current, that fault is tackled, but it is also still very difficult. So current disconnection of a circuit under healthy condition for maintenance under load as well as during fault is very difficult during the for the HVDC transmission. So this is the disadvantage of HVDC. What is the advantage? There is no reactive power issues, so all the complaints due to reactive power will be erased out. So that is the HVDC transmission. Transmission, we never generate DC. We always generate AC because synchronous generator has several advantages. Okay, and control is more easier. And what are the disadvantages of DC machines that you know? So we never generate in DC. We generate in AC. Generate AC, we transmit DC, so that the transmission issues due to reactive power problem can be controlled or can be removed. So that is the reason. So actually what will happen, we shall only use the transmission as DC, but we shall utilize the electric power as AC, and we shall generate the electric power as AC. So here I have shown as station 1 and station 2 because these two may change, or you may say sending end or receiving end. So anywhere, station 1 and station 2 I have written because the power may be transferred from station 1 to station 2 or station 2 to station 1. Okay. So in that way. So if I assume that power is transferred from station 1 to station 2, then at sending end there must be transformer to step up the voltage, because generation is generally at no low level, 11 kV, right, like that, maximum 20 kV, like that. Then that high voltage AC will be converted to DC using converter in rectifier mode, and this DC is controllable output. That means it is not diode based but thyristor based or other advanced switching devices based, right? Then that DC current will flow into the and reach to the receiving end, and receiving end there should be an inverter. So inverter is actually a converter where it is operating at an inverter mode. Then again we shall get AC and it will be usable. So we are converting AC to DC and transmitting it, and then again at the receiving end we are converting DC to AC and using it. But what will be the loss? What will be the problem in between these two? There are power electronics devices, so they are costly. Their regular maintenance is required. Regular monitoring control is required. At the same time, whenever there is a switching, then there will be transient. There will be harmonics. So now the harmonic issues will come. Harmonics were there in AC. Pure AC system was still there. There was harmonics due to the saturation of core. You know, when there is saturation of core, that means when we, if you see the phi I curve, if this side is I and this side is phi, then phi I curve is like this. If we do draw the normal magnetization curve, if you have forgotten, you see your first year notes. Then if the normal magnetization curve is beyond the knee point, the slope is more or less parallel to the x-axis, but not that. So actually what happened, before the knee point, the slope of the curve are more or less constant, or their change is very low. So B by H, that ratio is more or less constant, that we call mu. But beyond the knee point, that B by H is not constant. Every time it is changing. That's why inductance is changing. So that's why actually there is non-linearity. So inductance is changing. That means due to that, current will change, or induced EMF will, the inductor will change. So that will induce non-linearity. You have done the BH characteristics of the transformer in your power system lab in first sem. You have seen there that when there is a current, if when excitation voltage is beyond the rated voltage, the voltage transformer voltage was 110 volt. We have given, if we give 110 volt or near to that, then you have got some distortion. But near to 25 volt or 50 volt, you have not got. Why? Because transformer is always designed near to this knee point. So near this knee point means near to that saturation zone. So the nonlinearity will come. We have seen that one. So in that way, nonlinearity is there. If the nonlinearity is there, that means harmonics is there. This thing is not happening for the harmonics. This whatever thing I have explained you for the transformer code, it is not happening from the harmonic. Always you in the report you write that one, but that is not the thing. It is happening due to the nature of that magnetic material, the nature of that core, because all the magnetic molecules are linearized at the first stage, at the and near to the saturation there are no further magnetic molecules to get linearized. For that reason that comes. But due to that, actually the sinusoidal waveform, the current waveform become peaky in nature, that you have done in your power system lab, more or less. So this is not a pure sinusoidal, so it has a distortion. So if we want to resolve this current waveform into a number of sinusoidal waveform, then that way there will be some harmonics component. That's why there is harmonics, that we do by Fourier series or by signal processing. So that is the thing. Anyway, harmonics is there. Harmonic sources are there in the normal AC system also, due to the saturation of the cores. Even in the machines also in the same way. But that is not so prone like in the switching devices. In switching devices, harmonics, presence of harmonics will be far higher than the normal AC systems. So whenever there will be power electronics devices, then there will be switching issues, there will be harmonic issues. So harmonic issues, the current breaking problem, or the circuit breaker issues are the disadvantages of HVDCs, HVDC transmission. So these are two major disadvantages. Other some other disadvantages derived from there are listed in the book. You go through it. So this is the concept of HVDC transmission. Now in this um, topic, we shall not discuss the converter in detail, but because you have power electronics paper for that. But the part which that we shall need to relate it with the power system operation, I shall discuss only that much, and I shall discuss the converter portion for that to relate that one. So because it sometimes it's happened that this portion has not been covered in your power electronics class, and I shall not be able to proceed for that. So I have written made my note in that way, that I shall cover that portion, whatever required for my teaching, and then I shall go to the aspects of power system with the HVDC. Now, one more thing. Here I have told you that this sending station one, this converter will work as a rectifier mode, and the station two converter will act as an inverter mode when power is transferred from station one to station two. But now you know, by changing the angle, delta leading or lagging, we can reverse the power flow. So in that way, when power will flow from station one, station two to station one, then obviously this inverter in that case will be operated and as rectifier, and this converter will act as an inverter, and that is possible by changing the firing angle of the thyristor. And here I have shown you see the angle as the current as negative. Generally, we make the HVDC transmission with negative current. Why? How we can make negative current? We maintain negative polarity with respect to ground that for the DC voltage developed. Why? Because with negative current, it is seen that it has lesser interference well. So for that reason, actually negative current is adopted. Otherwise, there is no issue with the positive current. Now, what is the converter principles? It is only the recapitulation or one introduction. You have not, if you have not gone through it in your power electronics classes. If the power electronics is in this this semester or in the previous syllabus semester, where is it now? Your power electronics paper.
Previous semester, ma'am.
So you have already learned. So it is only the recapitulation. So I shall go fast. If you do not understand, then tell me. So actually, here you have gone through so many complicated converters. I think 6 pulse, 12 pulse, more than that, 24 pulse, like that. Here I have shown only simple 6 pulse converter. So the full wave rectification may be possible. So in that way, so these are the three thyristor in the positive side, three thyristor in the negative side. They are numbered in such a way so that their switching will be in sequence: one, then two, then three, then four, then five, then six. In that way, in this way, their pairing will be there. And here I have taken the R phase voltage as Em cos omega t plus 60. You may have used this one as Em sin omega t. There is no issue on that. I have taken in this way, then derivation, the expression of derivation will be easier. But if you use the ER equal to Em sin omega t and EY equal to Em sin omega t minus 120, the main magnitude, the derivation will give the same result. Okay, there may be some additional part. Okay, but the conclusion from the derivation, or whatever the our motive, or whatever be the expression, final expression of powers, that will be same. So that will be no issue. But I think this will be easier for me, so that I have taken in this way. So generally, I have seen this is not actually part of third year second semester class. It should not be, but I have drawn this one. So if I want to draw the waveform for EM cos omega t plus 60, that is for R phase, then obviously at omega t equal to minus 60, it is maximum, and omega t equal to 30, it is 0. So from there, you must identify the maximum and zero value, and from there, you must draw the R phase. Then Y phase, in that way you find out the maximum value, and from there plus minus twice plus minus pi angle you draw the waveform. In that way you draw the R phase, Y phase, then you draw the B phase. In that way you can draw the symmetrical waveform, because in this paper, in this part also question comes that what will be the converter input, what will be the converter output, you plot it, you draw it in the waveform. It has come. So there is a marks only on drawing. So you have to draw it properly in clear way. Uh, Now you see here there are three thyristor in the upper row. So 1, 3, 5. So any one of them will conduct, and then a positive voltage will be available at the positive side of the load. Then based on which this selection will be there, obviously among these three phases R, Y and B, the most positive phase will make that thyristor to be switched on only, obviously, when the gate signal is present, and the remaining two thyristors will automatically be commutated. So the most positive phase will come in the positive side of the load. So say R phase, for instance, for example, then this 3 and 5 will be automatically be commutated, because opposite voltage will appear across them. Then at the same time, when R phase is most positive, then there is no chance that negative side, the thyristor 4 will operate. So among these 2 or 6 will operate. So who will operate? So obviously most negative phase available between Y and B will operate. So let us assume that B is the most negative phase. Then this will operate. So it will automatically be force commuted. So the B phase will be available at the negative side of the load. So what will be the voltage available for that particular instant at the load across the load? It is VRB. In this way, that will change: VRB, VRY, then VYR, VYB. In that way, it will change, and we shall get 6 possible combinations within one complete cycle. That's why it is called 6 pulse converter. I repeatedly told that you should come in time. I actually give entry because all the parts of this power system performance are equally important. So whatever I told, that is written here. Now you see, I am not going to this explanation, this reading out. That is written here. Now you see, uh, let us. So we shall we shall um, discuss about say one complete cycle. So one complete cycle means 360 degree. So it will start from 0 to 360 or any 360 degree span. So here you see in the circuit I have told you at first, this is our common practice that R phase will be positive. Let us assume at first. Then R phase is positive. R phase is most positive at this moment or at this point, right? So either at 240 or at 160 as the waveform I have taken 360 degree apart. So let us assume that we start from minus 120 degrees. So if we want to get the 360 degree span, then I shall start from 120 degree and I shall go up to 240 degree, right? If you do not understand, then you must interrupt me. So at omega t equal to minus 120 degree, R phase is most positive. Then obviously the thyristor of R phase will operate. So thyristor on R phase is 1. So thyristor 1 will operate. Similarly, up to 0 degree, this R phase is most positive. So here also R phase is thyristor on R phase will be operate. So that's why this for 0 to minus 120 to 0 degree, this on positive side the R phase will operate. That's why I have written 1 here. So the positive current will be available on the R phase, right? Now you see on the negative side, so R phase cannot open. The R phase thyristor negative side cannot operate. So either blue phase 6, yellow phase 6 or blue phase 2 will operate. Now we have to see that if I see say in between minus 120 to 0 degrees, so for this span, which phase is most negative? You see there are two phases. From minus 120 to 60, Y phase is most negative, but after minus 60 to 0, blue phase is most negative. So from minus 120 to 60, yellow phase thyristor will operate, and from minus 60 to 0, blue phase thyristor will operate. So for that first 120 degree, minus 120 to 0, from the positive side, thyristor 1 will operate. On the negative side, for 60 degree, Y phase will operate. For next 60 degree, blue phase will operate, right? So this thing are written here. Similarly, if we go for next 120, so 0 to 120 degree, right? So 0 to 120 degree, next slot. So this much. So this much, you see now R phase is negative. So this R phase thyristor will be automatically commutated. We assume that source has no reactance. If there is inductance in source, then there will be some overlapping. That thing you have learned in your power electronics classes. That thing I'm not assuming here. Because I am discussing the simplest one. That thing can be taken care of by the power electronics issues or that part. So from 0 to 120 degree, the Y phase thyristor will operate, that is 3. In the negative side, there are two phases in equal part. So from 0 to 120, 0 to 60, up to this, from 0 to 60, the blue phase is most negative. So blue phase will continue. From 60 to 120, R phase is most negative. So the thyristor 4 will come. So in this way, it will continue. So that is written here. Similarly, 120 to 240, if I go 120 to 240, that means this span, then blue phase is most positive. So positive side blue phase will come. In negative side, for first 60 degree, R phase will continue. For next 60 degree, the Y phase will continue. Now you see on the positive side, each thyristor will conduct for 120 degree. Similarly, in the negative side also, each thyristor will conduct for 120 degree. That means when this from minus 160 minus 120 to 60 for this span, R phase will available on the positive side, Y phase will available in the negative side, so we shall get ERY. Similarly, ERB, EYB, that I have explained earlier also. So we shall get six pulses within one complete cycle. That's why it is called six pulse converter. Now, if we use here, we have assumed that firing angle is 0. That means whenever the R phase get positive, then firing angle is the gate signal is available, and we can thyristor can contact. But if there be any delay in gate signal, then there will be delay in output voltage. So the output voltage waveform will be available with an angle delay of alpha angle, and that delay will be same for each phase because they are coupled. We cannot change the delay angle from one phase to another. So in this way we can get the controlled DC voltage at the output. If we would have used the ordinary diode instead of thyristor, then this DC voltage would not be controllable. But why we need controlled DC voltage? Because we want to control the sending end voltage and receiving end voltage. Okay, so that's why it is needed. And one more thing, so in the load side, always one DC current will flow. But through the thyristor, in the R phase, this is the current, right? You see the R phase, this is the current, right? So in the transformer secondary of this circuit, when this R phase is operating, say for the example this and this, then for the load on the DC side, always the DC current is flowing. But what is happening to this transformer secondary winding? In transformer secondary winding, DC current is not flowing. In transformer secondary, the current what will be the direction of current flow? In this way, it will go. Then what will happen? For transformer secondary, the only the positive side will come. For the negative, for the remaining part, it will be zero, as I have shown there. In this way, right? So this will be the transformer secondary current, because transformer secondary current will not be DC. I hope you have understood. So when in the circuit, actually this transformer is supplying current power to this load, or we are transforming the AC power to the DC power. If we consider this converter to be lossless, then whatever be the power supplied by the AC side, that will be absorbed by the DC side, or that will be available in the DC side, right? So in that way, these two side power should be equal. So from there, we can relate how the AC power variation will change the DC power, or how the control of DC power will affect the AC side. That is actually our aim. So whatever I have told, I have written here also. And you know, in the DC side, there is one smoothing reactor also, so that it can reduce the ripple, and it reduces the harmonic current also to some extent. So in that way, there is a smoothing reactor there. And this transformer current also I have shown here properly. Now here we have assumed that computation occur instantly, but there will maybe overlapping also. The alpha angle delay also I have discussed. So what is the function of DC smoothing reactor? Decrease the harmonic voltage, prevents the commutation failure, smoothens the ripples. That also I have discussed. Now we want to relate the DC side power with the AC side power. So AC side voltage magnitude we know, RMS value we know, so we can calculate power VI cos phi. Then what will be the DC side power? We have to calculate or find the expression of DC current and DC voltage in terms of AC quantities. So here in the waveform, you see from -60 to 0 degree ERB is available. So what will be DC average power? This integration of this ERB over this cycle twice pi by pi, in that way, using the equation of average voltage, this one. 6 pulses are available within twice pi within one full cycle, and this is expression of 1. So we shall integrate this one over twice pi, and the 6 pulses are available. So we are using for 6. So average This is the average. So this is the total available by the total time period or angle period. I hope you know this. So here, why I have chosen ERB? You can choose anything. ERB will give you the give us the me the expressions more handly. So I shall do that. I have done that one. With any other expression, ERY, what EBY, whatever you do, you will get the same thing. So ERB is available from minus 60 to 0. So from minus 60 to 0 ERB. So what is the ERB in terms of phase quantities? So let us write at that one, because I have started with the phase quantities ER equal to EM cos omega t plus 60. So from there we can get an expression of ERB, right? So ERB will be this one. So here EM is the magnitude of phase voltage. So if we want to find out DC voltage, it will be 6 into ERB, because same pulses are available 6 times, and total time span or angle span, here I am integrating over angle. So that total angle span is twice pi, so it is divided by twice pi. So now just put the expressions and do the integration. Whatever I do, so we shall get 3 root 3 EM by pi. 3 root 3 EM by pi, this expression we can write as VD0, right? No problem. So VD0 2 sine 30 cos alpha. So then we shall get VD0 cos alpha. Now if we use some other thing, we shall get VD0 cos alpha plus some time delay like that. Sin omega t plus cos alpha, some other expression. But actually you will get VD0. So this 3 root 3 by m, 3 root 3 m by pi, you will get it in any, if you start from ERB, EBY, whatever. So DC voltage is VD0 cos alpha. Actually, it is in terms of AC voltage 3 root 3 EM by pi cos alpha. Now EM actually the magnitude of phase voltage. Now you can convert it into magnitude of line voltage, magnitude of RMS value of phase voltage. This conversion you can do multiplying by root 3 divided by root 3, or multiplying by root 2 dividing by root 2 to convert it from phase to magnitude to maximum to RMS, or from phase to line. In that way we can do. So here actually this is the magnitude, so I have converted into the RMS value of phase voltage. So this similarly from line voltage also you can do EL. I have given here also in terms of line voltage. That is nothing but a conversion, nothing more than that. Anyway, so what is happening to the transformer secondary if we consider R phase? Then we have seen for R phase, when the R phase thyristor is operating, only then in that case R phase current is available, right? So it is a square wave. It is conducting for 120 degree, then there is a 60-degree gap, then again it is conducting for 120 degree. Now if we draw only for R phase, so it will be the R phase voltage in transformer secondary, and this will be the R phase current, right? Now if we assume that ER equal to EM cos omega t, if we want to assume that one, then we shall shift the axis, right? Then the axis will be here like that. Then you see for positive half cycle, IR equal to plus ID from theta equal to minus 60 to plus 60, right? Then IR equal to 0. Then again from 120 to 240, there is a IR equal to minus ID, right? Someone is there. No. So here I am assuming ER equal to EM cos omega t, right? So EM cos omega t means here is the axis. So up from minus 60 to 60, it is the plus ID, and from 120 to 240, it is minus ID. Now here the secondary current is not sinusoidal, but it is a square wave. It has half wave symmetry, but it is not sinusoidal waveform, it is a square wave. So we cannot use the formula VI cos phi for active power, because it is not a sinusoidal waveform. That is applicable only for the sinusoidal waveform. So here we need to convert this square waveform, which has half wave symmetry, to an equivalent sinusoidal waveform of 50 Hz frequency. then only we can apply that Vi cos phi. So that we can do using harmonic analysis. So here I am calculating only the fundamental component because we are interested in fundamental power. Similarly, the harmonics component may also be calculated, and we can calculate what are the harmonic issues, what are the THDs, but here I am not interested on that, so I am not calculating. So fundamental component is root over a1 square by b1 square plus b1 square into tan inverse b1 by e1. What are this a1, b1? A1 is the 2 into average of I theta cos theta, whatever be the function of I with respect to theta or omega t multiplied by cos omega t, average of that, and b1 is 2 into average of I theta sin theta. Now, if anything has any waveform has half wave symmetry, then it has only cosinusoidal term. The sinusoidal term does not come. This thing, right? So only the a1 will be there. So root 2 by pi minus 62 plus 60 will be available only id cos theta d theta, because minus 62 plus 60 it is available, and 2 into that because it is in average in the negative side also available. So it is in that way. So we shall get one expression of id, whatever is that, right? And b will be 0, obviously. Now what will be then the AC current? This is the A1. From A1 we have to derive what is the fundamental component of current. So it will be root 2 root 3 by pi d tan inverse b1 by 1 came 0 degree, so it is 0. So what is the RMS value? This is the magnitude. RMS value will be this by root 2. So this by root 2 is the RMS value. So this is the RMS value of fundamental component of current in phasor. So now RMS value of voltage is available. So RMS value into RMS value of current, RMS value of voltage into cos of power factor angle between these two will give us power. Now load current is Vd by RL. So we can get the expression of load current also. Load current, this expression I have written because this may be required for the numerical example. Now you see AC side current and DC side current will be same. So AC side current is 3 Vi cos phi because these are the phase quantities. Now what is the DC side current? Vd into Id. Simply Vd into Id. That I have not written here. It is better to write anyway. Now this PDC is Vd into Id. There is no cos phi there. If I write in terms of DC quantity, what will be, because in DC there is no part, no phase, so total DC power will be equal to 3 phase AC power. So this Vd we have derived, that is Vd0 cos alpha, or this one, and Id we have derived this one, right? Id is I have written in terms of RMS because here we need Id. So Id is C pi into IRMS by root 6, right? In that way. So here, now see in both sides there is E phase, obviously that will be there, IRMS is there. Now we can relate this cos phi with the alpha or phi with the alpha, right? And we shall get that cos phi equal to cos alpha. Now you think, cos phi is the power factor angle of AC side. Phi is the power factor angle of AC side, and alpha is the firing angle of the thyristors, right? Now for the lossless converter, this relationship will be maintained. So cos phi will be cos alpha. Now you are making alpha equal to 0 degree. That means power factor on the AC side is 1. If you are making alpha equal to 10 degree, then there is a power factor on AC side. Okay. So it is developed due to the converter operation. It was not there. So if it is there, that initially the power factor of the AC side was 0, but you have used a firing angle of alpha, then a one cos 10 will be derived there, will be developed there. So to compensate that 10 degree lagging, if I said positive side inductive, then we have to use 10 degree leading to compensate this much of reactive portion, is not it? That's why reactive power devices is required in the converter, in the HVDC stations, since still it is developed, it is generating, it is converting AC to DC, But due to this conversion procedure, there will be reactive power deficit on the AC side. That may be required. That may require the compensation, right? In that way. So now this is very easy. Now, if we, to decide to make some comment from here. So AC BDC is this one, and P and QAC is this one, sine alpha. Anyway, and cos phi equal to cos alpha, right? So in place of cos phi, we can easily write cos alpha. Now, obviously, now you see the AC, only the active power part. So if the alpha is within 90 degree, then the power generated will be positive. If it is beyond 90 degree, then power generation will be negative. That means up to alpha equal to 90 degree, that a converter will operate as an rectifier. Beyond the alpha equal to 90 degree, that converter will act as an inverter. It will generate power, transfer the power in opposite direction. That means it will generate AC, right? So that's why when we change from station 1 to station 2, only the firing angle will change. If we want to configure one station as sending end, we shall we shall set the alpha less than 90. If we want to set that station as a receiving end, then we shall set alpha more than 90, right? In that way. And then at alpha equal to 90 degree, there will be no active power, right? In that way, we actually discard the DC circuit. If there is no active power, there will be no DC power. Then current through the DC system will be zero, right? We can do that one. And at alpha equal to 0, P equal to P max in that way. 1 minute. This will be 5. There is some copy paste issues. Not this symbol. Now, similarly, at alpha equal to 90 degree, there will be no real power. Obviously, we shall never reach this situation. Then there will be total reactive power problem, reactive power consumption of the circuit on the AC side. We shall never reach that situation. And when alpha is greater than 90 degree, P is negative. That means converter will act as an inverter. Alpha equal to 120 degree, P equal to minus P max. Then inverter will give us maximum power. So we can configure the converter as rectifier or inverter. Now, in the power transmission system, the HVDC transmission line is termed as link. It is same as conductor, but they are termed in power system terminology as link. So there are 3 types of link in HVDC. One is monopolar. From the name, it is clear monopolar means only one link is available with the negative polarity. Single polarity may be there, but we use negative polarity. Okay. But and return path may be ground or C. So one return path is required, and return conductor is saved. Conductor cost is saved. We using the return path of ground or water. But it is only possible if there is no human hazards or any hazards if we use that path. Otherwise, we cannot do it. Right? And one more thing, one more reason why we go for the HVDC transmission. For a long transmission line, if we transmit a transmission line for a long distance, and if we make it at no load, then capacitive effect is very huge. Not only the reactive power issues, even at no load condition, there may be capacitive effect, and that may create Ferranti effect and the high voltage problem. To get rid of that problem also, this HVDC transmission is used. So to cross a river from the base of the river, for that reason also this HVDC is used. I have forgot to mention that one. Now, when this return path is not possible through ground or sea, then your metallic return is required. So this is the HVDC monopolar link. Always it is negative. Positive. This upward side of thyristor means it is converter, rectifier mode, and downward side means inverter mode. But this may be opposite. Now, obviously here total power will be transmitted through one link. So there may be same disadvantage like the single circuit of AC. So if that is transmitted through a single circuit, then their reliability will be less. Okay, if it is out of order, then total load will be disturbed. So it is divided. It may be if it is possible, then it is better to divide it into two equal parts. That's why I go for the two parts. So for two parts, there is uh, bipolar link. The power is divided and sent into two parts using two conductors. So here obviously, so one is positive, another is negative. So the configuration output load connection on the positive side of the link and the negative link are totally opposite. So if the one link is out of order, say this positive side, then this negative link can never cater this load because the circuit connection is totally different. It's not it. One is supplying positive current, another is supplying negative current. At the same time, and at the same time, interference is also high. That's why we go for the homopolar link. We go for the both negative link. And negative link, I have told you that interference is less. And since we are using positive current, same positive current and negative current, then this return path may not be required also if the currents are equal. But for the homopolar link, I am not reading all this. So for the homopolar link, always the same configuration is there, all negative current. Now, if the one link is out of order, then the other link can cater that load easily because total reconnection is not required. So this is the advantage of homopolar link, and homopolar links are mostly used in the in HVDC transmission. Okay. The slides, whatever I have written, you read it. If you have any problem, then you ask me in the next class. Now, something I want to mention. So, in case of HVDC configuration, let me go to the. Say here, say it may happen that in DC side, huge voltage is like required, 750 kV. It is not possible that one conductor may give this 750 kV. Then what is done like battery? The positive side of one converter is connected to the negative side of one converter. I hope you know that. So in this way, converter outputs are connected in series on the DC side so that we can get a high voltage. Similarly, on AC side, each converter should get same voltage, is not it? Same EM. That's why the AC side of the converter should be connected in parallel, right? So AC side should be connected in parallel, DC side will be connected in series like battery. So, and that I have written here. And why the HVDC applications are used, that I have discussed at the first, that is written also here. And asynchronous link, what does it mean? Sometime it happen now that in a village there is a generation, there is no local generation, solar or wind, but that is not maintaining 50 hertz. Now if you want to supply their power, then you cannot supply 50 hertz AC. Then what you can do, you can convert that AC to DC and you supply there, and you can convert it into the local frequency. Otherwise, without frequency matching, we cannot transmit the power, we cannot supply the power. So that may be one requirement also. Sometimes it requires, because sometimes we want ideally to operate the system at 50 hertz frequency, and obviously there must be some norm. That's why it is 50 hertz frequency. Grids are forced to operate at 50 hertz frequency. Still sometimes there is a limitation because the to supply the electricity to the consumer is the first priority. Sometimes it is required to supply the power at different frequency. Then we cannot connect an HVDC an HVAC transmission line there because it will create the instability issues. So we have to connect the cables, sorry, HVDC in that case. Now, actually, in a HVDC station, there are some other supporting uh, um, instruments also, or components are also there. Obviously, there will be circuit breaker on AC side. At the same time, filter will be there because there is switching devices, so there will be harmonics, so filter will be there. And reactive power source is required because cos pi equal to cos alpha, so reactive power devices will be required. On DC side also, there may be some harmonic imposed with along with DC, so filter will be there, and smoothening reactor will be there. So in that way, these two I have shown my blue and red dotted line. These two are the component of the, so both all the components are present, same component in the receiving end or sending end or station 1 and station 2, and they are not in side by side. Obviously, this dotted line of transmission line is indicating that they are far away from each other. And so in a HVDC power transmission system, how the power transfer will be controlled? Obviously, the sending end we shall set alpha less than 90, and receiving end we shall set alpha more than 90. Then we can transmit power. And if we want to reverse that, we just configure alpha in opposite way. So in that way, we can control the power flow. And if we want to discard the circuit breaker design is very difficult in DC because we have to discard that much of current. So the circuit breaker is available. We have to dissipate that energy in a secondary L circuit, inductive circuit. That option is there, but it is very difficult. So it is not readily available, very techno friendly like the AC circuit breakers. So that's why actually the application of HVDC is limited. Otherwise, if we replace all our transmission lines by HVDC, that would be ideal. But that's why these applications has been limited. So advantage, disadvantage I have written here. I am not going through it. Skin effect I forgot to mention. That's why I have no, I have noted here something. But if you see the book, there may will be 10 advantages. But here I have written only 4 because that those 10 will be that the subpart of this 4, maybe some important advantages I may skip also, but I think these are the major advantages and disadvantages. Okay, but advantages, disadvantages list you must go through you must read from the book also. And these are the some HPC systems available in the India. There are far more than this right now. I have listed this, so this only these 3, but far more that are available here. Okay, and nowadays in India. So these are the HVDC transmission. Okay. From next class, I shall start load flow analysis. So from next class, for load flow analysis, you must read the compensation part and the transmission line part. I just take a review. That will not be directly related with the load flow analysis, but that will help you to understand the modeling of power transmission line that you have learned in your third year power system planning design class. The modeling of long transmission line pi equivalent model. Take a recap of that. Go through this before coming to the next class. Okay, that's all for today.